Next talk will be given by Harald Kübler from Stuttgart, who was so well determined to be here that he skipped the group hike in Stuttgart in the Alps.
Wow, thanks for the introduction, and of course, thanks for inviting me to come here. And essentially, currently, I'm really just continuing the series of imperfection in the positronium. As in my case, we're really talking about nitric oxide, so we are even adding a dipole in positronium core. And yeah. I'll tell you about our experiments we're doing in Stuttgart, and talking about doing in Stuttgart is really the right expression, as it is not only our physics institute that is involved, but we've also got two institutes from the electrical engineering department that really contribute largely to the research we're doing here. And well, essentially, if you want to get engineers involved, you've always get their interest in the topic. And for our case, it is really the targeted application of what we think is a possible way to build a trace gas sensor, or more precisely, crack gas analysis sensor for nitric oxide. And yeah, like nitric oxide, except for the positronium acid. It is an important molecule in your body, and it's a signaling molecule for inflammatory diseases. That means lung cancer, asthma, all those diseases make you exhale a little bit more of nitric oxide. It is also important in the blood pressure regulation. And it is a way to fight bacteria in your body. So there is a real medical application for node sensing. And this applies for humans, but also other mammals especially. So yeah, this is really a large application area. And just to give you a number, so half a human exhales something like a part per billion concentration of nitric oxide, and it can go up by a factor of 2,000, and that's the picture of potential disease. And so far, with all the methods that are used in medicine, you need a pretty large gas volume to be sensitive enough. But with medical research, it's pretty hard to get half a liter of air from these guys. It's pretty hard. And that's where the new idea of the sensor comes in. Yeah, what are we doing? In principle, I got already a pretty nice introduction by Frederick. We are also taking our gas sample. It can be pure nitric oxide. In the end, it will be a mixture of several gases. We send it through one of our measurement cells, which is here. We then do next is we do a laser excitation. In our case, it is a 3-photon excitation up to Rydberg state. And in our case, we're measuring at up to 1 millibar. So we get a lot of collisions. So we don't do field ionization. We ionize the molecules by collisions. And that allows us to extract the current here, which is then in the end our measurement signal. And yeah, that's what the setup looks like. So it is a little bit smaller than all the setups you're usually used to. It is really what you see is this size, and as everyone else, we skip the size of the laser setup. But already here you can see that we have a group flow setup. We got our electronics here, our electronics down there. And we've got force windows glued on the side. And that's another nice thing for all the people working with alkali atoms. Nitric oxide is highly reactive, but there are glues that can withstand nitric oxide. So production of the cells is way easier than what you're used to for the alkali atoms. Plus, we're working in through flow, simplifies the containment also a lot. Yeah, we've got a PCB board on top. There are amplifiers, there's a lot of electronics on top. And we've got a counter electrode on the bottom side. And also, we are working with CW lasers. We can get narrow line in there, though we're still partially Doppler problem. It's not Doppler free. We only have a reduced Doppler width in the whole signal. And just by changing the pressure in the cell, we can control the collisional broadening and all the collisional effects with the background gas. So we restrict, so far, we restrict ourselves to the vibrational quantum number to be 0. And all the thing that's hidden in the electronic contribution, as I already said, we had a really nice talk. That's, at least for the formalism I'm showing you, or the things I'm showing here, that's all hidden in the electronic contribution. And then, in addition to that, we have a significant rotational contribution in our molecules, especially as we are not cooling our gas. We've got a distribution over all or a lot of rotational states, and we have to pick them by our first excitation laser. So in principle, we've got electronic part, including angular momentum, with the rotational part, and then we just get the Rydberg series shifted by the rotational energy. And what we can do is our laser excitation now that H state up here determines essentially where within the Rydberg manifold we can address our states, and then we just have our red or last laser really doing the addressing, and this allows us to at least have an idea which stage we're really talking to. If we do this in a rather broad scanning of several nanometers, well, it's molecules, you see several lines, and even you can identify maybe 2 series of lines in here, and that's exactly what you're getting. The one series for one rotational quantum number here in yellow, and if you just look at the other rotational quantum number, it matches the yellow. Not easy to see in the plot, but this is mainly the remaining lines, but I think you believe me, and this is really the separation into spectra, or in 2 Rydberg series I was talking about. So now what we can do is we can zoom in, just narrow down our scan on, for example, this combination. It is nice. We've got 2 lines nearby, both of the rotational series, and yeah, I don't have to introduce dark maps. We already heard about them. And this is roughly, yeah, what I've shown, let's say, a year ago on the last CATMIN conference. And of course, we get our dark maps. There, it's clear you can identify the hydrogenic manifold up there. We get several states, and if we take a closer look, we can even see that there are avoided crossings, and we can see the interaction between the different states. But, well, I told you, we've got a collaboration with the electrical engineering guys. So we use the recent time to make use of that. We just got the next generation of our cell working. It's, yeah, the electronics changed a lot. The geometry of the field plates changed a lot. and it looks different. We had to play some electronic tricks, way more shielding and field compensation areas around the cell. And now with these changes, well, we also changed the state we're looking at. That's just mindly about we just broaden the scope. Yeah, this is the new result. So talking to engineers sometimes really does help. And now we're down to a line width of sometimes down to 60 megahertz in a thermal sample of NO, accessing the full start map here. And you can still see that there's some shadows among the lines, but if you do the precise calculation, every line you see there is a manifold of several lines. So this is real, this is not an artifact or a bad measurement. And even there we can again zoom in, at least in my opinion, with the beamer is good enough, you can really see that we can resolve all the crossings we've got in there. And this will, of course, allow us to look at coupling strength between the manifolds and do some, wait for some calculations, math, and then try to compare. Yeah, so generally just improved our resolution, I think, obviously, significantly, and more important, unfortunately, Rosario is gone, but Pussy is still there. Another thing that might have been not as obvious, we managed to remove a lot of the background we had around the zero electric field spectra, which means we can do more sensitive measurements on lines that are very weak, or maybe even the molecules Rosario use. And that's actually where we will continue our work on. We still a little bit of background we've seen there. That's what we have applied. We want to really look for, very, very weak signals. And that's one of the challenges for the electrical engineering guys right now. Nevertheless, we can do something else, and that means we can really increase the pressure in our cell pretty easily. That means we can really look at different densities just by turning on a knob. And that was the other joke. Someone said there is no bottle you just open for getting positron patterns. There is a bottle for no, we can make use of that. So, but first of all, I want to compare it to measurements we did a few years ago. And if you compare the setup we were using at that time with the setup I just showed you, well, the differences are mainly in colors. But at that time, we could elaborate rubidium measured in the background of additional gas here. Here it's all gases, but that's exactly the difference. That one, well, we can look at what we saw in rubidium. Well, we just use the mixture of rubidium and argon, for example, then we see pressure dropping. Of course, but we also see a clear pressure shift. That's been known for really long time, and this is really just to verify that we know what we are doing. The same can be done for lithium and nitrogen, and that's why a lot of the sensors, atomic clocks and other sensory modified transit time problem, they use a background gas where they have increased the mixture of nitrogen. These two problems almost no shift. Also, that can be verified. Now, the big question is, that's ongoing work right now. is rubidium, is the picture we were using that rubidium and nitric oxides are just positonium atoms. This is really true. And then what we can do is just prepare the same thing for nitric oxide. And as I said, it's ongoing measurements. And at least we can confirm that also there with pressure broadening is broadening. We get shifts somehow. Either we gotta check our measurement, and this is preliminary data, or we can we state dependent shifts right now, which is probably we're looking into, especially as we point out that there is one line, the orange one, that isn't shifting at all. We really look into it. We really think it isn't shifting, but it consists of two lines. So there is something going on that we got to investigate what it is. And of course, we can do the comparison with the nitrogen in our setup. There we see the same broadening, but also almost no shift. No, we didn't use the wrong background cast there. We definitely checked. So with that, I just want to summarize my talk. So I told you that nitric oxide has an application. That's the way you can easily get the engineers to join your team. We did the measurement with our electronic readout technique. We can look at the Stark effect. We can really go down to 60 megahertz resolution in a thermal sample, allowing us to access high rotational quantum numbers, for example. We can go all the way down. We don't have to apply only high fields. It's really, we've got a full range of spectrum accessible. We can see the pressure shifts and we can see pressure broadening compared to rubidium and get similar results at least. And with that, I want to thank you for your attention. Yeah.
So a few years ago, Ed Grant at the University of British Columbia showed that in a supersonic ether layout, it's quite easy to form a plasma. And I wondered whether you think that plasma effects could be playing a role in the Gaussian measurements.
I think we're extracting the charges fast enough. So there is no way that the plasma would really build up. We really see the linear current.
So those measurements are made with the E field on them.
Yeah.
These last pressure shift measurements. So if you have a fluid spectral gas, you only change the density of the curve, but if you have NO, then you also change the Rydberg density. So
Yeah.
did you correct? For that, or did you
At least if we look at our lines, the lines don't, they just move, they don't broaden more than what we measured there. And this is consistent with what we've seen with the NO broadening roughly. So we assume that it's not a Rydberg interaction. If you just look at the densities and also do the calculation, the probability that we have a Rydberg is really, really small between having Rydberg ground state interactions in there.
So the first realization that N2 did not lead to Boring, that was Amaldi and Segre.
Yeah, exactly.
So
yes.
Nice. But so when you extrapolate to zero pressure, you still get a width about 20 megas. I think I got. So where does that come from? That's the Doppler.
That's Doppler. Yeah, yeah. So we've got 3 lasers, but they're not completely Doppler compensating. There is a remaining K if you sum them up.
But did you detect the light coming out, or
no? We really detect.
in other words, you would use our trick to image the fluorescence, and then do the Doppler for you.
Yeah, yeah. Now we're looking at the current directly we're getting. So your talk was interesting, and actually the idea with the several electrodes made me think about talking to the electrical engineering guys if they could structure something like this, because we are also going in one direction with the beams, and having the electrodes set up, maybe we can see a difference. So that's definitely something I'll ask them to do.
Now, it's surely.
I was just wondering if you have any problems with your glass cells charging.
We see a little bit of that on the side walls, but that's exactly the work the electrical engineering guys have been looking into. The electrode structure in there, or the ground plane structure in there, is pretty complicated, really, to make sure that yeah, electrons are, and the positive ions are mainly hitting conductive surfaces.
No. So if there are no more buses, then you only have to power and power.
Slightly over time, we will try to come back here precisely at 10:30. But
Well, regard to copy. And the law and the state, the one thing and then you would have a certain range. Yeah, exactly. So what you really want to range for that that would be long, like that would be long range, the range of electron. Well, you can set that, you have lots of different bands. Yeah, you can set the different from. So if you only have two bands, you can basically get it track by cutting off the mapping. Yeah, exactly. And this we we're looking at H2s, and then we found that we can exclude these field boards that are range of one bore radius more than that. Yeah, and here you go, it's completely different. That's interesting. So since we get a equal to take a flight off, we get a file and I didn't see the description of that. Yeah. That would be why doesn't you obviously still have but I can see that because of the bond, yeah, 40, there's so low signal, only enough, and then we 24, but maybe it's not. Yeah. Yeah, I mean, my thought was a problem with that is all going to change the intensity of the further with the notification. But that's maybe something. But there's only one thing very nice.
And we were being that because of the high pressure that we have in treated that we will do this superb.
And when we
With the electric bike, we start at AC discharge and we put the dielectric somewhere between, and that makes a very good generator.
Yeah. Okay.
They were told in the boat.
Well, that's what it is.
We don't really do it because we don't have the density. It itself, where H2, we went to the BC, and then we could do H, but we could not do B. Because B would stick at the wall. And so he had to medium flow into the deck, and then B was in there. Yeah, because yeah, sure.
Technology they have back then, and we wouldn't know actually possible to design and experiment.
I think there's a lot to do because people more or less abandon by thinking it's too hard. But I think now it's become easy.
But then you set the bar very high.
We are not close to densities that would be interesting for conversation. Yes, the problem is that so we're weak signals to the states, and then you're going to focus, and then your AC star shifts that become the dominant point. So we had a phase when we were trying to do two photon CW spectroscopy of Rydberg transitions, and it's very difficult to see any signal, and it was always older than we hoped for because of the AC. Yeah, yeah. I mean, even one photon transition to around the CW is not totally easy. Yeah, I think so the transit time, our transit time is maybe 2 months after. We have the experiment repeated with the valve has been 25 years. And then what makes our experiment possible is that we sync the frequency of our experiments to mains. In other words, you have the pollution of the mains fluctuation in all your electronics. So I this single photography, I think this is what we're going to do for a while. It's just incredible. Well, a little bit. We should come to Zurich. We try to organize something. This semester we have already our program maybe next year. And it was the problem. I think only very much that's what we want. We had a proposal. On hydrogen. We had actually an ITAMP symposium on hydrogen that we were going to organize before the pandemics. And this was seen by an ITAMP, and I just thought we were saying so that would be kind of a application.
So that would be looking at all we don't have how I people a lot of
they had this laser Lanan alpha laser that they were using basically laser pool.
Yeah.
I don't know how far they went, but this will also touch something. Yeah. I think we were also. Yeah. Yeah, and it's so the good thing, he says it, we have a meeting, and we'll be optimistic that this
So now people are debating on really.
Yeah.
You start something,
How you started
something with this.
But anyway,
Yeah.
They're not looking, they what's a lot of measurement on the ground stage, we move on and trying to so we have the groups in France and then explode. And small systems, they have become factor. This Schiller in Düsseldorf with a stage 2 HD plus supposed to do the good advice that they want to do something. Yes, it's like I hope it's increased green that was involved. Well, hopefully. Yeah, hopefully we can do that earlier. So we got to get it's
Well done for doing the blind analysis, because I think that one thing that's not being done enough by the people that do something like that.
so yeah, but you see that sometimes you would find artifacts quicker.
Well, I know, it's not really
For a long time, we have not realized that when we apply 0.84 centimeter, you think the 2s doesn't ring, but actually it does. Yes, so that we only recognize. Later, had we not blind, we would have seen that.
Yeah, but even if you underline the big distraction, you don't need to go back and look at what all the rules are, but I think you still have to. I think it's really important that you.
But for the
You don't come to number.
it lets you,
Especially with this discrepancy that is in social media.
it sets you in a different frame of doing the planning of the town. You just do it differently. But for me, I mean, I have to say, I would far prefer know what we're measuring. I also just to assess it, and
Yeah.
this is somehow nerve-wracking. And we were actually really, we measured this, we took the difference.
Yeah.
The part of 0 and 1, this was less than the part of.
So you did the opposite. So the fact that energy is such it's very wide, but there's still the temptation that, you know, that the old center is here, the new center is here.
You find it very different.
Yes, exactly, which is where you're what's exactly where your bias of thinking, right? It's the head towards.
So yours measured the 2s interval, and not the 1s.
Yeah.
The measurement of so much practice.
Reason practically from
The thing value from the one you go.
the air class almost. It's almost as inclusive.
yeah, it's also exactly where you so if you don't do
I
it,
think if you things in, it would be one of them.
yeah, if you don't do a blind analysis, the problem is you get that way, you stop.
But
You stop thinking about it at that point, so you even then you're applying a bias, right? You bias.
But what for us is difficult for me, not so much for Simon, is that when you do one way in the methodology, then you should definitely learn. But if you explore a new way to do it,
Yeah.
it will make your life more difficult.
Yeah.
But we see that sort of the final measurements that we have.
I think it's being among the main reason for the environment, that's one point.
But I mean, it's on more than target and that's not. I would agree with
But it's not really good. Journal says they learning to take
no. This journal says it should not be on Google. Because they say that the government. introduce virus.